Hello, students. Today we'll be working on your second day of related rates problems. We'll be looking at equations that have more variables in them. And sometimes you have enough given information that you can work with all of those variables, but sometimes you're going to need to search for relationships within the problem that would let you reduce your number of variables. And so we have that example today. We're going to look at a cone. I have a picture of a growing pile of sand, and you can see that we have a cone forming right here. That's what we're going to look at for our problem today. So as we read through it, we find that we have the growth of the volume of the conical pile being 10 cubic meters per minute. We have this relationship that the height of the pile is 3/8 of the base diameter, and we're asked to find how fast for part A the height is changing, and then for part B how fast the radius is changing as the sand is falling from the conveyor belt. So first of all, you're going to need to know the volume formula for a cone. So that is volume equals 1/3 pi r squared h. And so you should first think ahead. If you do the derivative with respect to time, then you would need, first of all, you'd have a product. You'd have to do the product rule, which isn't necessarily something that's going to cause problems, but it will in this one because you'll have dv dt, you'll have in this process a dr dt, and you'll have in this process a dh dt. And in the given information, only what I've underlined in red is a rate of change of anything. Everything else is either what we're trying to find or a relationship. So you just don't have enough variables. So we're going to concentrate on part A. Part A wants us to find the height. And so we're going to use the relationship that was given to us, that, and I've underlined that in blue. The height is 3/8 of the diameter. Now, we're really not interested in the diameter. We're interested in the radius. And by the way, the diameter on that cone would be going across the circular part of the bottom. So we know that a diameter is twice the radius. And so we have the height being 6/8 or 3/4 of the radius. And you should be prepared to have that relationship go either direction. So you should also solve it for r. You could multiply by 4/3 and have r equaling 4/3 h. So we'll keep that off to the side as information that we might need. Since in part A, we are asked to find the rate of change of the height, we need to keep h. We need to keep the height in the problem, which means I need to substitute in place of the r. So volume equals, and notice I'm doing this before I do the derivative, 1/3 pi. So I want to take r out, put 4/3 h in its place. Remember that that gets squared. And then I'm going to simplify that. So 4/3 squared would be 16/9. I can multiply that by 1/3 pi. I'm going to get 16 pi over 27 h to the third power. And that's going to be the equation that I'll use to find the rate of change of the height. So I'm going to take that and do the derivative with respect to time, which will give me dv dt equaling, all right, now I can multiply the 3 by the 16 pi over 27. You could reduce it. I'm not going to. So 3 times 16 is 48 pi over 27, and then it's h squared. And because the h is not time, we have to have dh dt. Now we can substitute in our other given information. So we were asked about the height when the pile is 4 meters high. So when h is 4. So we were given dV/dt, that's 10, and that is cubic meters per minute. And by the way, I know that that's dV/dt if for no other reason than the units. It's cubic meters. That cubic is a measure of volume. All right, and then we have 48 pi over 27. We have the h, which is 4 meters. And this is going to be squared, and then dH dt. Now at this point, you could be using your calculators depending on how much of this you need to show. I'll show just a little bit more. I'm going to have that 10 cubic meters per minute. And then I'm going to multiply 16 times 48 pi over 27. That gives me 768 pi over 27. This is in meters squared, and I still have my variable dH dt. So I can multiply by the reciprocal of 768 pi over 27. You can multiply that on both sides. The meters cubed and the meters squared will cancel to just give me meters per minute. So that's 270. I'm going to move up here. So 270 over 768 pi, and this is in meters per minute. And that is actually what we were asked to find, dH dt. And then we're just going to work on making sense of that. Well, and also we have to remember that we were asked to give our answer in centimeters per minute. So to get it to centimeters, I'll have to multiply by 100. 100 centimeters is a meter. So that would be 27,000 centimeters per 768 pi meters, or excuse me, minutes for our dH dt. And at this point, I'm going to switch to a decimal approximation. So that would be 11.19. We'll go to the nearest hundredth centimeters per minute is what the rate of change of the height would be. So dH dt, 11.19 centimeters per minute. And that takes care of the unit change and having us find the rate of change of the height. And I might go ahead and draw that in. That would be the rate of change of this height as the sand is going from the conveyor belt to the pile when the height is at 4 meters. All right, now that takes care of part A. Usually part B is just a matter of substituting in to a different variable, substituting in a different value for the same variable. But in this case, in part B, we actually are asked about a different variable. And so this one's not quite as easy. We are in part B going to have to start over on our derivative because we're asked to find the rate of change of the radius. So I'll clear the screen, and actually I'm just going to erase a little bit of this, but you'll probably want to, on your papers, create a new area for you to be doing this work. So I've cleared out where I've got the volume equals, or or to the point where I have volume equals 16 pi over 27 h to the third. That is not going to help me because I'm supposed to be finding the radius. So I'm going to have to actually go clear back to my beginning volume formula. And this time, instead of substituting for the r, I'm going to have to keep the r and substitute for the h. So the volume would equal 1/3 pi r squared, and then taking h out, that's why I have my work over here in blue that I wanted to keep, I can substitute in 3/4 r. So we can simplify. Your 3's will cancel, and so we'll have pi over 4, and then the r's would add exponents. Volume equals pi over 4 r to the third. All right, so this is what we'll be doing our derivative of. So the derivative with respect to time, and again, this is part B. So we have dv dt equals, and then 3 pi over 4 r squared dr dt. So remember to bring your exponent around, reduce your exponent by 1, and then have your dr dt. So as you continue to think about what we need to do, we need to be able to substitute in our value of the radius. But it doesn't appear that we have been given that information. So now you have to go back to your given information and the relationship, and the fact that the height is 3/4 of the radius, and the radius is 4/3 of the height. So we can actually use that last line. The radius is 4/3 of the height. So when the height is a 4, then our radius is 16/3, and that would be in meters. So we can substitute in for the radius using 16/3. So that relationship information becomes very important. All right, so we have 10 cubic meters per minute for the rate of change of the volume, and then 3 pi over 4. Oops. And then we'll have our 16/3 meters, and that is squared. And we're looking for the rate of change of the radius, the dr dt. So if you square 16/3 and multiply that by 3 pi over 4, you'll end up with 768 pi over 36 meters squared dr dt. And then our other side, 10 cubic meters per minute. So we can multiply again by the reciprocal and solve for dr dt. Notice again that the meters cubed and the meters squared will cancel to give us just meters. So, and meters per minute. So now we have 360 over 768 pi. And again, those could be simplified, but I'm not going to do that. This is in meters per minute as our dr dt. It does ask you to give it in centimeters per minute. So you'd have to multiply like we did on the last one by 100. So that would be 36,000 over 768 pi centimeters per minute. And as a decimal, again, approximating to the nearest hundredth, we have 14.92 centimeters per minute as the rate of change of the radius. So many of the problems that you'll have in this second round are going to require some sort of substitution. You'll often find that there is a relationship based on similar triangles. So as you encounter those different shapes, if you're not sure about that relationship, you can ask because probably you will need to reduce your number of variables. So good luck on your homework.